Alright, so for the first part of this video, I want to give a very quick and generic kind of history on the atomic model, meaning, right, the model of the atom. This is very much an overview. There's a lot more details to be had, but that's not really the purpose of the video, so I just want to kind of get the idea. So we didn't start with the plum pudding model. That wasn't the original model, but that's what we're starting with, okay? It was a model called the plum pudding model. And basically, we knew that there were these little negative things called electrons that we could isolate out of atoms. And since there were negative things that we could isolate out, but overall atoms were not negatively charged, there must be a positive charge as well. But since all we could do was isolate these little negative things, they came up with a plum pudding model, which was basically atoms are, right, a blob of pudding where the pudding itself is positively charged, right? Maybe you can think of this as like yogurt with blueberries in it, where the yogurt itself is positively charged, but inside of it are these little negatively charged blueberries, right? This was the plum pudding model, that just this general blob of positive with these negative electrons in it that can be removed. So that was, a thought. Now, Rutherford did the gold foil experiment. Again, we're not going to get into it, but what he found was that when he shot positively charged particles at atoms, right? So he took a positively charged particle and he shot it through a piece of gold foil, which is made up of atoms, and he found most of them went completely through, went right through completely unscathed, but some of them went and they were completely rejected, right? They came and they bounced and they went the complete opposite direction. So what that allowed him to deduce is what he called, or I don't know if he called it, but what we kind of call the nuclear model, meaning that there is a nucleus, there is a very dense, positively charged core, and the electrons, right, are just kind of around the outside, and most of the atom is empty space, right? So he's getting closer. He's getting closer there. So now he says protons in the middle, electrons on the outside. So that makes sense. While most of those things were able to just go right through the atom, no problem. But occasionally when he hit that nucleus with his positively charged particle, it got shot, in crazy directions. Again, we're doing a very quick overview. All right, then Bohr came along, and Bohr found out that there were energy levels, all right? So it's not like these electrons are just kind of willy-nilly running around doing whatever they want. They actually have energy levels, meaning you have your positively charged proton in the middle, and then there are these rings around it, and the electrons stay in these rings. Now, getting closer, right? I like to call this the solar system model, right? It looks kind of like a solar system, closer, and honestly, pretty much as good as we need to get right now for what we're going to do. It does get a little beyond this, and we get from orbits to orbitals, which turn into three-dimensional shapes. But for us, for right now, we're not going to get into it. And the last thing to happen was a guy named James Chadwick, figured out that this middle here is not just protons, it's actually neutrons as well. So kind of the last model here is you have this nucleus that is filled with positively charged protons and neutral, which I'm just going to use as 0, neutrally charged neutrons, right? Positively charged protons and neutrally charged neutrons. And around that are electrons. And this is kind of the model that we're going to work with for this class, for this lesson, is this idea where protons and neutrons are the nucleus and they're in the middle, and electrons are flying around on the outside and they are negatively charged.
Alright, we had a few technical difficulties, but we're back. So where we left off, we realized that the atom has a nucleus, and inside that nucleus are positively charged protons and neutrally charged neutrons. And then all around the outside are these negatively charged electrons. Again, this is a great model, not particularly accurate, but that'll work, right? And they're going around the outside. Okay, so every element, every atom, is defined by the number of protons. And if you look at a periodic table, such as this one, you'll see hydrogen is number 1, helium is number 2, and it just continues to count 3, 4, 5. Right? It adds by 1 as you move across the periodic table. That is called its atomic number. So again, if we just pick an element, we'll pick nitrogen, right? On this periodic table, now all periodic tables are formatted a little differently, but on this periodic table, we'll do that. It looks like this. All right? So we have two different numbers here. You're always going to have an integer, which is the atomic number. Atomic number. And sometimes you have an integer, but generally a number that has a decimal involved, and this is the mass. All right, you'll hear it called atomic mass, molar mass, whatever. It's mass, atomic weight. This is the mass. So here's the thing. The atomic number is the number of protons. So nitrogen has 7 protons. 7 protons means nitrogen. That's the definition of nitrogen. So if you have nitrogen that then loses a proton, you're not nitrogen with 6 protons. If you don't have 7 protons, you're no longer nitrogen. End of conversation. Okay? So that's really, really important. Now, the mass equals protons plus neutrons. Right? So in order to find the number of neutrons, you would just subtract them. Now, you might be asking yourself, well, if I subtract these, I get a decimal. I get 17.01. I'm sorry, 7.01. How do I have 7.01 neutrons? You don't. You can only have whole numbers of neutrons. And that's where isotopes come in. And so we're going to talk about that. Let me just give you a quick explanation. This is an average. So what they did was, if you take 1 trillion nitrogen atoms and get the mass of 1 trillion nitrogen atoms and then divide by 1 trillion to find the average, you will get 14.01. Because some weigh 14, some weigh 15, etc., etc. So when you average them out, you get 14.1. That being said, when we're trying to find neutrons, we can't use the average atomic mass. We have to use the very specific mass of a very specific isotope. So let me show you what I'm talking about here, right? So if we want to do the nitrogen 14 isotope, and we want to find protons, neutrons, and electrons of that isotope, you can do it. Now, anytime there's only one number written next to an element like that, right? And I just completely ignored the 7, right? The 7's gone. You don't put the 7 in there. And why is that? Because remember, the definition of nitrogen is 7 protons. So you don't have to put that number there anymore. If you see the N, its atomic number is 7, it has 7 protons. End of conversation. Now, this isotope does not have a charge. You'll know there's a charge because there'll be like a number written in the top right corner up there or up here or something. This doesn't have a charge. So what that means is the number of positively charged protons and the number of negatively charged electrons have to be the same. Because if they weren't the same, then the thing would be charged. Since it's not charged, they're the same. And then finally, to find neutrons, it's just the difference between the mass and the protons. So in this case, it's also 7, right? But another isotope of nitrogen called nitrogen 15, right? If we do this, right? It's nitrogen, so it has 7 protons. There's no charge, so it has 7 electrons. But if you look, it has 8 neutrons. So what is an isotope? Right? An isotope is a specific atom of an element, right? It's going to have the same number of protons as long as it's uncharged, the same number of electrons. It's just the neutrons can change, right? Neutrons can change. Right, let's do one more. So for instance, if we do chlorine 35, right? Again, you go to the periodic table, it's right here. You find chlorine. Its atomic number is 17. That means it has 17 protons. Since there's no charge on it, it also has 17 electrons. And so, again, the neutrons is the difference between the protons and the mass, which in this case is 18. And that's all there is for finding protons, neutrons, and electrons in an uncharged isotope. Alright, so the last thing here is finding the protons, neutrons, and electrons in an ion, or a charged atom. So they come in neutral, which we already talked about, but then they can also be charged, and they can have a positive or a negative charge. Now, if you remember our kind of rudimentary but effective model of the atom was it has a positive middle, right? The protons in the middle are positive, with neutral neutral neutrons, and that's the nucleus. And then around the outside were the electrons that are negatively charged. All right, this is a kind of a rudimentary model, but it works. So, if something has a positive charge, that means it has more protons than electrons. If something has a negative charge, that means it has more electrons than protons. Right? That's how it is. But remember, atoms cannot gain or lose protons because they're defined by the number of protons. Right? So if I say lithium, no matter what else happens, lithium has 3 protons. Nothing else matters, right? And again, if you look at the periodic table, lithium is number 3, so it has 3 protons. Now we can worry about the rest. So if lithium has a positive 1 charge, which will be shown as an exponent like that, and a mass of 7, remember, neutrons are just the difference between the protons and the mass. So it has 4 neutrons. But it having a positive 1 charge means that it has 1 more proton than electrons. And since you cannot change the protons, you have to change the electrons. Therefore, this would have 2 electrons. The 3 and the 4 give us the 7. The positive 3 and the negative 2 give us the positive 1. All right, let's do another one. Let's do bromine with a negative 1 charge and a mass of 80. Kind of out of room there, but that's an 80. So again, bromine is atomic number 35. The numbers are irrelevant when you're looking for protons. Protons are always just the atomic number, which bromine is 35. That's it. Now neutrons, remember, the difference between those two. So 45. Right? 35 plus 45 gives you 80. Now last, for the electrons, because it has a negative 1 charge, that means it needs 2 more electrons, one more electron than protons. So if it has 35 protons, it needs 36 electrons. Right? So the 35 positives and the 36 negatives give you a negative 1. The 35 protons and 45 neutrons give you a mass of 80. Alright, let's do one more. Let's do iron with a charge of positive 3 and a mass of 56. Drawn all over my table here. Okay, so again, iron is number 26 on the periodic table. So again, those numbers are irrelevant for protons. Iron is always 26, 26 is always iron, no exceptions. Now, these two have to add to that, right? Protons plus neutrons equals mass. So 26 plus 30 will give us our 56. And now for the electrons, again, positive 3 means it has 3 more protons. Right? If this was neutral, I'm going to erase this in a second, so don't write it down. Right? I'm just going to write 26 here, kind of in parentheses. Right? If it was neutral, it would have 26 protons and 26 electrons, but it's not. Right? It needs 3 more protons than electrons. So you have to take away 3 electrons because you can't change the protons. I can't say it enough times. You cannot change the protons. So it has 23 electrons. Again, 26 plus 30 is 56. 26 positives and 23 negatives gives you a positive 3.